what if it's not symmetrical like butadiene? What if we have this system, or this alkene? Well, at this point, if we treat it with acid, adding hydrogens to the outside to form allylic cations, we can form two different cations. And so it remains to be seen, and let's actually draw these two on different lines here. It remains to be seen which of these is the more stable cation, because we know that the kinetic product has to originate from the more stable of these two cations. So let's see which one's more stable. Each of these has a resonance contributor. Okay, and we can find those with one arrow to form a pi bond. For each of these. And we can kind of analyze this system. And so if we do, we see that we've got a secondary allylic cation here. We've got a primary allylic here. Okay, so it's allylic in that it can resonate with a double bond, and there's a primary carbon, there's a secondary carbon. Well, the other cation that's possible is secondary allylic, and then this one's actually on a tertiary carbon, puts the positive charge, so this is much better. Okay, so tertiary allylic is even better than secondary, is better than primary. So this is the most stable cation. Okay, the most stable cation is here, so it's going to have an easier transition state, more than likely, for the formation of this cation, and it will be more present in a lower energy solution. So in a kinetic conditions, this will be present most preferentially because the cation's lower in energy, and even the transition state to form it is lower in energy, so the proximity effect still applies. So in this case, since this is more stable, we add our chloride 1,2 versus 1,4. So 1,2, where did we start? We started here. So the 2 position is right here. So the 1,2 product, we'll put a chlorine here. And this will be the kinetic because it arises from the lowest energy intermediate. We didn't care about this for butadiene because there was no second possible cation to check. And then we look at the 1,4 product, and the 1,4 product would put a chlorine here. Notice how the 1,4 is actually less stable. It's di-substituted, so there's only 2 R groups here coming off that double bond, and there are 3. This is a tri-substituted alkene, so it's more stable. So 1,2 is more stable in this case, but we can't just declare that product also the thermodynamic. We must look at the other cation and see if it gives us a more substituted product. So let's add chlorine to these and see what happens, because in a high energy situation we would be able to access both cations in the solution. The 2 position would be as shown. Where does the action begin? It begins right here. Okay, so there's the 2 position. And what product do we get from that? This product is 1,2. It's not kinetic because it arises from a higher energy cation. And then here we have a 1,4 product. None of these two, or neither of these two, is more substituted than the original 1,2 kinetic product. So it turns out that this is both the kinetic and thermodynamic product. And if we look at this by an energy diagram, the system that we have described starts with the starting material, raise that energy to form the cation, and we form two different cations. The kinetic product is going to arise from the lower energy cation, and turns out it's the lowest energy overall. It's a 1-2 kinetic. It's also the thermodynamic, because the other cations, or the other product for this one, is higher in energy, and then both of these are also higher in energy than that original. So we've got two intermediates, and let's code these with color here. So we've got the first set of intermediates that we formed. Okay, and we know that resonance hybrids describe these, and they are right here. And then the products are all given here for this process. The starting material, we started with this Diene, and we treated with acid to form carbocations. Rate determining step is always the formation of the cation, and then we follow the rest of the way.